The thing I want to highlight again that okay, so one of the problems but one of the things that we have noticed is that some people are rushing for their missions, which is not necessarily a good thing because a lot of people make mistakes. So Tomb Theory was open last, Friday, but it's not due until like tomorrow or until like Friday or something like that, right? Reason is because you're open early, then you look at it, but there's no real need to actually go and do it. People are rushing it and making mistakes, okay? Because actually some of the things that we need to do, like map, is going to be covered today. Okay, so we would like to encourage you to basically, take your time a little bit more, okay? And don't rush and learn stuff. Okay, that's it, The paths, okay, a few of you fellas have gotten nasty notes from me, because it turns out that the SC Academy is quite interesting. I can see every single thing is going on. Okay, so if you don't do your paths, whatever, you're stuck somewhere, I can't know, I write a nasty note to tell you, whether you continue, whatever. So the point now is that the paths are, okay, I would say paths are very important, but then fundamentally, they are designed to help you learn. So if you don't do the paths, then I think some people are a little bit lost. Okay, so I will encourage you to do your work properly and consistently. The missions, don't rush. Okay, so the thing is that this class is all about process. That means, okay, I'm currently in the process of trying to come up with midterm exams. Okay, so okay, one thing I want to highlight is this. Okay, among you there are people who are who are not programmers before you, who didn't have any program background. Okay, so the thing to note is this: what you really need to do is to make sure you are familiar with the interpreter, the Docker scheme. Okay, so it turns out that programming is not the same as math, right? I mean, it's programming. Okay, computer science is applied math. Okay, but programming is not something like math, whereby you just look at partial solutions, you try to learn how the thing works, and you get it right. There are people who do that because some of the solutions don't compile. I mean, they have errors when you run them. Okay, so that means that people are just happily typing out code. Okay, so people are just typing code and then pretending that they work. Alright, so the thing to note for those people who don't have background is that you need to spend probably more time than the rest for the beginning of this first few weeks, just to make sure you understand, you get a feeling for how the interpreter works. Okay, that's very important. Okay, it's important for your practical exam, obviously. Okay, but it's also important for the written exam because the way that it works is that to become a good programmer, you essentially need to basically learn how to get a kind of feeling for how programming works. So you must be able to mentally run programs in your head. Okay. So basically, the guys who are rushing the things, okay, just know that okay, at the end of the day, people always complain that you spend much time on this class, but then I just want to remind you that there are other classes out there. Okay. And you're not expected to spend all your time on this class. Questions? Okay, so just make sure that you know that. Okay, now, so today we're going to go into more detail about how to work with data structures. Okay, so last week we started off with the cons, car, and CUDA. Okay, so today we'll cover a few more topics that is related to data structures. Okay, now, so recap. First of all, you have this thing called list, alright, which is really kind of basically a sequence of cons. Alright, a cons is what? It's actually a pair, right? It's this box there, right? It's this box with 2 pointers, right? The first pointer is the car, second pointer is the CUDA. Okay, and it turns out that if you have a special sequence of cons boxes of this form, basically it's a whole train of cons boxes, terminating with a null. This thing is called list. Okay. Now, if the last pointer is not a null, right? It's some random pointer to something else, then it is a valid data structure, but it's not a list. Okay, a list has a definition, it's defined as a whole chain of these guys, whereby the last thing is a noun. Okay? Question? Anybody? The question is, why is it that we use cons with a dot, and when you use this, there's no dot? Okay lah. Not really. Okay, so the point now is this, right? The point now is that if you take this thing and you actually write out based on the dot notation with the dot, right? You can actually, it kind of makes sense, okay? Unfortunately, it looks damn annoying. Okay, so basically, if you do 1 dot open parenthesis, 2 dot open parenthesis, 3 dot open parenthesis, 4 dot now close parenthesis, then close, is damn annoying. Okay, agree, right? Okay, so because this thing is not, this is a special structure, not a list. Okay. So basically it's like synthetic sugar again to make it look a bit prettier. Yeah, the same thing. Except that, I mean, the dot form will basically annoy the heck out of you, right? Okay, you will see lists a lot. Okay, you will see lists a lot. So basically it's a very common list structure. And using the so-called the A dot B notation is damn annoying looking. Okay. So the similar reason why you want to do the let instead of a lambda applied to the expressions. Because although they're equivalent, right, one form is a lot more annoying than the other. Clear? Because what? Yeah, okay. So we can talk about that. Okay, but anyway, not to worry, you will not be tested on what this thing will look like in exam. Don't waste my time, okay? Hello, that's so free. Okay, so do I care? I actually don't care. I mean, about these things. Right? These are things that, something I care about, something that I don't. These are things I don't really care about. Okay, question? Okay, so the null pointer is either this empty parenthesis, this parenthesis, nothing inside, or null. Okay, this thing. Alright, so again, this is a synthetic sugar. You have list of this old form, gives you this whole thing. Alright, because the cons printing will be too annoying. Okay, next, the kind of CUDA. Okay. Car obviously returns the first pointer, the element pointed to by the first pointer. CUDA is the second element. Now test whether or not that object is a null pointer. Null means nothing lah, okay? Simple, Okay, length of element. So let's do a quick exercise. Suppose you have a list, okay, of elements. Length does what? Returns the number of elements in the list. How would you do this? Recursion, very good. So basically, so you're first year, so you take us 3 years to graduate. Right. After it's now 5 years. So 8 years from now, remember nothing in my class, never mind. Remember 2 things. What? Managing complexity and recursion. Very good. Passed already. Okay, so first thing is what? Is recursion. So first thing to do is base case. What's the base case? If now what? 0, right? Okay, no brainer, right? Same thing. Okay, so one thing you have to understand is that today, to be honest, there's nothing new, nothing really new, okay. That means everything that you will learn you will see in terms of operations and stuff like that, same old stuff, okay, but applied to lists, okay. So it's what you call old wine in new bottle, right? Okay, so it's the same old stuff that you used to know. We are applying this in different contexts only, So if not, do what? +1 line CUDA, right? Okay, because the idea is that you take one piece, you chop out, add 1, and then after that you just CUDA down the list, okay? And then you go next one. So essentially it's the same. Okay, this is exactly the same. I mean, okay, it looks a bit different, but the principle of this thing is no different from the counting of the digits, right? Except that it's 100 digits, you lop off using what? Remainder, right? Okay? No, not remainder, quotient, right? Use quotient to lop off the digit. Here you just use the CUDA to CUDA down the list. Okay, what's the length of this thing? 4, Okay, you can count, Very good. Okay, pass. This one? Okay, very good. Alright, now suppose you, again, same old thing, right? You know, you have enough of this recursion, don't feel like doing recursion in iteration. What do you do? What's the first thing to do? The alpha function, right? Okay, what do you call it? I can't remember what I call it, something. Okay. So, you have got 2 elements as your state variable. So what's the next thing? Base case, which is what? Now or what? Items, return, and right. Otherwise, you call the iter, increase n, and you CUDA down the list, right? Okay. Call iter, increase n by 1, and then you CUDA down the list, right? Okay. And then after that, what is the last thing? You call iter with the initial conditions, which is what? 0 and the items, right? Okay. So simple. Okay, so now let's look at another operation. Okay, by the way, length, append, all these things I'm going to show you, they are all predefined. So right now we are basically redefining stuff that's really predefined for you. Okay, but this is for practice. We always do these type of things in the scheme. We redefine all stuff, but just for kicks. Alright, so the next question is this. Suppose you have two lists, you want to merge them. Okay, so you take lists like 1, 2, 3, 1, 3, 5, and 2 and 4. Okay, you append it together, you have this whole list called 1, 3, 5, 2, 4. Simple? Alright, this is what you want to do. Okay, so the question now is how do you do something like this? Alright, so let's look at the strategy. Suppose, actually the answer is obvious, right? How you do this? By recursion, right? Somehow, okay, every single thing that you see, pretty much the answer is by recursion, somehow. Okay, almost given, okay? So you have two lists, 1, 3, 5, 2, 4. Okay, so what do you do? How to recurse? I also know but like, how would you do that? So the thing is that basically the general idea is very simple. You take the first list, you keep coding down the list until you find a null, and then you smack the rest behind it. That's all, right? Correct? Okay? So, what do you want to do? Okay, so that's the general idea. Okay, let's take a look. Okay, recursion, obviously recursion. Okay, so if list 1 is empty, then how? Obviously you return list 2 because nothing appended to something, it's just the second thing, right? Okay, good. Suppose the first thing is not null, then how? Then you take the first element, you put it down the list, right? Okay? Otherwise, I suppose I know how to append the list, the tail of list 1 to list 2. And this is what I do. I simply const the first car element onto append of CUDA of the string, right? Alright? I say again now. So what I do is I const the first element onto the append of the CUDA to the list 2, right? It's quite obvious, true, right? Okay. Alright, so let's take a look. Okay, so define append list 1, list 2. Okay. First thing is what? Is the base case. Okay, so very good. Now I'm also training you all to basically, think like a functional programmer, because you do recursion. First thing you do is base case. Now, this is important training, because suppose you do your practical exam, you forget base case. My God, you're gonna waste all time. Okay, so some of the things should be very obvious to you, and you shouldn't have to waste time anymore. So base case will be what? If list, which one? If now list 1, return list 2, right? Okay. If not, then how? Const car list 1 to the append of CUDA list 1, list 2, right? Okay. This looks a bit mysterious. Are we all on the same page? And don't be shy. Like I said, it's important that you all follow me because once you get lost in this class, it's a bit painful. So I do have some time. Are we okay? Okay. Who here understands this? Understands this. Okay, so because normally I ask to understand, then all very shy. Sir, behind. This is Eugene Ang, right? You didn't put your hand, so how? Huh? What? Can't hear you. You put up, okay. Okay, okay, so this is good, Alright, so let's take a look, Define A is list 1, 2, 3, okay. B is 5, 6, Okay. Let's say append AD, okay. So obviously this is the answer, okay. This one will be what? Opposite, right? Okay, simple. Okay, this one, what is this? Recursive or iterative? No, okay, it's obviously recursive procedure. Recursive means process. Is a recursive or iterative process? What is the gate operation? Const, Are you clear? Okay, it's not always plus minus, okay, so you must make sure you understand this. Okay, order of growth? So no. So okay. So the order of growth, the n will be size of list 1. What's the order of growth? Order n, right? Are you clear? Okay. Okay, so can you do this creatively? Okay. Anyway, this is for your homework, so figure out. Okay, so now this one obviously is recursive. Do this iteratively. Okay. Now the thing to highlight is one, do not mistake append for const. Okay. So this thing is what? Is 1, 2, 3, and some weird thing like this. This is not. Okay, so this thing is not the 1, 2, 3, 5, 6. It's this weird thing. No, you wouldn't. Yeah. Never mind. Just set this first. It just won't. This is what you get. Okay, you won't get this. Just know this. Okay. Now let's try another thing. Again, reverse is given to you. It's a predefined procedure, but we'll just do this for kicks. How would you reverse the list? Naively. Yeah. So first step. Base case is what? Now then do what? Return now lah, right? If you just now list, obviously now lah, okay? After that, do what? You take the first one, you const it to the, so very good, You take the thing, you const the thing, reverse that, right? This is true, right? Correct? Obviously, I get in trouble. Why? You say, I say again, you take the first piece, okay? You const the reverse of the second of the CUDA to the first piece. So you reverse this one. Okay, so obviously wrong, very good. Why is it wrong? The first one is a now, that's the thing. So the problem, why wrong? Wrong is because of this. Now let's look at this. Okay. So the way to see whether it's right or wrong, I just try out. Okay. So suppose you reverse based on this code. Reverse, you do this. Okay, yeah, this. The answer will be this one. Okay. What's the answer you want? The answer you want is 5, 4, 3, 2, 1 as a list, right? But then if you do this kind of thing, you get what happens? You have this weird looking thing whereby so this answers your question. So this whole thing prints out as a funny dot structure, right? Because it is not a list. Okay, so basically the list representation is like synthetic sugar of these things, when the whole thing is well behaved. Okay, but this is a very, very ill behaved. It's not a list, right? So you print out in this form. Okay, and it's a bit annoying. Okay, so something is obviously wrong, but obviously you can do this right. Okay, now so the point is, sorry, this example also means that this problem is quite evil, and don't always believe me when I tell you things. So I don't always tell the right things. Okay, sometimes I tell the wrong things, just make sure you know what the heck's right. Okay, so this is wrong. How would you fix this? Append, right? Okay, oops. Now, so the right way of doing this is the following, is to append reverse of this thing to what? Car of the first thing, right? Correct or not? You sure not? You need to be a list of the car of the first thing, right? Okay. So the lesson here is the following. Is that you must know for each operation what in the world is doing. Okay. Append does what? Appends a list to a list. Okay. The car of the thing may be a list, but it'll be wrong, or you do the wrong thing. You come to some element. So what you need to do here is that you need to wrap the car into a list first, and then you append the thing, and then things will be fine. Okay? Otherwise, the thing will blow up. Okay, if you don't believe me, you can get rid of the list. You can get rid of this list here and see what happens. Okay? Okay, so the thing to understand here is that this list of car is different from the singleton object. Okay? And you need to use the append itself. Okay, this is the general fix. Now, let's try it out. Suppose you do this. Okay, so let's try out. So, one of the problems is that you may find some of this code of being a bit unobvious, right? A little bit obscure. So in exams, I use an obscure looking thing. You don't know what heck's going on. How do you figure it out? You trace the procedure and do yourself a favor. Don't use a list of 35 elements or something. That's very fun. This can die. So you basically put some examples inside there that is kind of manageable, right? So you get some sense of what happens. Maybe start a simple one element. Then okay, one element you understand. Maybe one element is not enough. Do two. still too simple, do 5, whatever lah. But don't start off with 35 and then, you know, life is good. Okay, think count change to 35, don't until you can die. Okay, so the thing is that, what are the key things to understand is that you look at a piece of code, it's kind of obscure. This is actually a piece of simple code. This code is actually quite parsable. Okay, I'm not so kind, sorry. Exams will not be so parsable. Okay, so you may have to actually write out the thing and try to figure it out. So for example, you do the following, you open up reverse because append, reverse 2, 3, 5, 2, 3, 4, and 1, right? Okay, see the 1 is a cast, but I wrapped it in a list. Okay, and this thing obviously can expand itself into this thing, and this thing. Okay, so essentially, after a few rounds, you get this whole thing, right? This is what kind of procedure? Process? Recursive, right? What is the default operation? Append, right? Okay, again, so default operation is not a plus in this case. It's not a con, it's a append. Alright, and now you reach this point, right? Okay, and then what happens after that? You will go to the next level, which would be, okay, from here, actually, I'm skipping steps. You reverse, actually you go to now, right? But okay, but then you know that reverse of 4 is a 4, right? So essentially you become append 4 and 3, right? Okay, you append these two guys, you become this thing, and this thing, right? Okay. Okay. So this is kind of how it works. Now, what's the order of growth? N. Who says N? Who says, okay, who says N? All ahead. Who says more than N? Who says less than N? Okay, who says N? Sure or not? Are you sure? What's the order of growth of pen? Oh, so how? Okay, so this one is an interesting case of a seemingly linear thing, calling a linear thing, so the net will be a squared thing, right? Okay, and then what is the space? Add, okay, very good. You all clear? So this thing would be a squared, order of growth time is squared because of the fact that it's a linear recursion calling a append which is actually linear. Okay, so this is a squared thing. Alright, so the thing is that let's try to do this smarter. This one is not a very smart thing because it's order n squared, right? So can we do it smarter? Our answer obviously is yes, right? And the way we can do this a little smarter is to use iterative process. Okay. So next thing, what is the next step? Helper. What are states? How many state variables? 2. Why? Okay, the general approach here will be what? You have a list. Okay, the general approach here, what's the general approach? Essentially what you do is this, you're going to have 2 lists, right? One is the beginning list, one is the now list. What's going to do? You're going to take one element of this list and move into the second one, right? Okay, so let's take a look. So the iterative helper has the following state. What is the next thing? Base case, which is what? Now first list, return second list. If not, then how? Helper calls to what? CUDA the first list, and then cons to the second list, right? CUDA the first list, cons cast the second list, right? Okay? What? Not append? Why is it cons not append? Con or append? No, but can work or not? Can I just replace the cons with append now? So okay, the lesson here is this, that you must make sure you know what in the world append is doing, what in the world cons are doing, and they're not doing the same thing. Okay, here is the con. So what are the things that you all need to, those of you who figured it out, then very good for you. Those of you who haven't figured it out, it's normal. You go back and stare some more. Okay, and make sure you figure out what the difference between append and the cons. Okay. Now what's the last thing? Call the helper with what? With now. List and now, right? Okay. So this is the general way of doing it. Okay, let's take a look. How do you do this? You call reverse this thing. You have the what? Helper, the list, and now, right? Correct? Then the next step is what? You take the first list, you do what? You cool it down the list, and then you do what? You take the car, and you const to the second list, right? So you have what? 2, 3, 4, and 1, right? Then you take out what? The 2, and you const to the 1, right? So you have this. So actually it's kind of obvious, I mean, in the end, you basically take take the first guy, you shove to the second side, and you just reverse itself. And then by the time the first guy is empty, you return the second piece, right? Output ugly one. No, you just return the second piece. It's not ugly one. No, this is not ugly one. You think about it, it's not ugly. It's nice and pretty. Okay, you see, the thing is this, it's ugly only if, okay, let me explain to you the ugliness. Now, if you have a bunch of guys, a bunch of const boxes, the last pointer is a null, will be pretty ugly. It will be pretty, okay, I say again. So if you have a bunch of const boxes in the whole sequence, the last thing in the whole sequence is a null, the printout will be pretty. Because this structure is a proper list. If the last thing is not null, then it's a lot of dots all over the shop. Okay, are we clear? Okay, because then it's not a proper list, right? So essentially, this thing is nice and cute because the last thing is starts a null. You consting the 1 to the null, right? So it's a proper list. And then when you const something to a proper list, it's still a proper list. So the whole thing will remain pretty the whole time. Then you have a open parenthesis, a null, and then you got some stuff It's okay. Yeah, it's a proper list. Okay, later you see something else. It's called a tree. It's a list of lists. Okay, more fun. Okay, don't worry. Relax. You're jumping again. Okay, so let's recap. So this is the recursive version of reverse. Right? What is the time? N squared, right? Space. Okay. Now this is the iterative version of reverse. What's the time? Space. Okay. Clear. Alright, so we are actually covering old ground now. We're not doing anything new today. I mean, the only thing that's new is to show you how to do car encoder, but you could pretty much do the same thing with like quotient remainder kind of thing. Alright, it's just applying, I'm trying to reinforce the same concept of recursion iteration, basically through a different example. Okay, so another thing is this, how many of you still feel a little lost? Or are you perfectly comfortable with lectures now? How many are you comfortable with lectures, the pace? Yes, comfortable. Who's comfortable? Who is still a little bit uneasy? Samantha's still uneasy. Okay, it's okay. Anybody else? Okay, so okay, don't feel shy. Okay, generally this is the thing. Okay, you all know that I put up all the lecture slides way before, right? Okay, those of you who basically are having harder time following lectures, then you should go read the slides before you come. Okay, you may not understand everything, but hopefully once you read everything, you have a better overview. So you pretty much, the comfortable ones pretty much can follow at the pace. You can see the slides on the day itself, that's fine. Okay, but hopefully some of you who are new to programming, okay, this is an exercise you need to do. At the end of the whole class, hopefully you will look through the first 2 weeks of lecture and it looks completely trivial. Okay, obviously, I mean, if you think back to the first few weeks, obviously it wasn't trivial. I mean, you look at it, all the stuff, it takes time to kind of to figure out, right? But you will realize, you understand, you get smarter when in a few weeks from now, hopefully, if not, then you're in deep trouble. If all these are right, before the final exam, when you review the first few weeks of slides, it should be quite obvious. Okay? So this is the power of scheme. Okay, let's take look at an example. Suppose you want to do the following, which is this thing called scaling. You have a list of stuff, okay, 1, 2, 3, 4. You want to scale it by a factor of 3. Okay? So how would you do this again? Recursion, obviously. Okay? We also know. See? So easy at this class. Okay? You can do it yourself. Okay? Now, so recursion, we do this. How would you do this? First thing will be what? Base case is just what? Now what? Items, return what? Okay, very simple. No brainer. Next thing, it's not now, then how? Const don't car first const car what? Sorry, const star car factor, right? And then do what? Scale list of the coder, right? Okay, so you coder down the list. Okay, so basically this general technique is called codering down the list. It's quite no-brainer one. I mean, you'll be doing this over and over again. Okay, it's just take the first piece. Okay, general idea here is this: you have a list. Okay, the recursion here is that you basically take the first thing, do stuff with it, and then you recurse down, coder down the list. Okay, that's the general idea. Okay, so this is it. Next, let's do something else. Let's say you want to square the list. You feel shook, and then you want to do 1, 2, 3, 4, make it become 1, 4, 9, 16, right? How would you do that? Again, same thing, right? So how? Then square what? Square car, right? Okay. Other than that, you do what? Square list of the cooldown list, right? Okay. All natural, all very okay. Obviously, okay. Nothing is this. Make sure that, okay, when I do these things in class, it's completely obvious, no? Sadly, well, not sadly, good for me, good for you, okay, you give good ratings, I'm very happy. But the problem here is this, things that are obvious in class, when you actually do it yourself, it may not so obvious. Okay, so those of you who are really on top of material, don't waste time. Those of you who basically think you're having some trouble, one of the things you want to do is try to replicate the things I do in class by yourself. When you open the scheme, you tell yourself, okay, I will write reverse. And you figure out how to write reverse from first principle. Okay, the way you see do it like magic, simple. But then, if you don't have enough practice, some of you may have trouble. Okay, so make sure that, okay, all of you can actually do this in your sleep. Because the exams are always so easy. Okay, this is the basics. And the thing is that you must spend some time now to make sure these things are completely natural for you. Okay, anyway, you've seen these two examples. Obviously, this is what I'm trying to tell you, right? What's the key lesson here inside? It's called sama, right? Why? This thing. So essentially, it's pretty much the same thing. Okay? So when you see two pieces of code, they're pretty much the same thing. Tells you it's some higher order procedure, right? Okay? So this is the thing. Okay. Right. Okay. So next, there's this operation that you want to perform. Okay. Given a list of elements A, B, C, D, right? Oftentimes you want to create a new list. Okay, that is obtained by applying a function f onto each element, right? So this gives you a new list of the form fa, fb, fc, fd. Okay. It turns out there's a name for this operation. This is called a mapping operation. Okay. So obviously we also have a version of this thing called map, whereby you can take a procedure, you apply to a list, and the output is a list. Okay, that is a list consisting of elements of the original list. Okay, with the function prop applied to each element. Yes. Prop is lambda. Correct. Okay? Good. So, again, how would you do this? Okay, this is the thing. I asked you to do obscure things, but you apply the same simple first order principles to solve this. How will you do this? Map is what? What's the first step? No brainer. It's what? Base case, right? Whereby you check what? Items to be now, then return. Okay. See, no brain, right? Just do it. Just think at all. Next one. What do next? Cons of what? Prop on the car, right? Okay. Do what? So you map on the cooled down list, right? Okay. Are you seeing the pattern now? Okay, there's no real smartness here. We're just doing the same thing we used to do before. Okay. Alright, so scaling list by factor, how would you write this? No, it's map, right? Map lambda what? X star the factor, right? Okay. So you do this will be map of lambda x star x factor of the items, right? Okay. Simple, So just now when we did scale list, it's this big piece of thing, recursion, everything. Now what we do is that we just take the map operation, you apply it, put in the lambda. Okay. So this is where you see all the anonymous procedures coming in, because it's damn annoying to have to name the lambda and then put a lambda and whatever, right? So now, from now on, from here onwards, you should all be very familiar with the lambdas. This is anonymous procedures. Essentially, the lambda is what? It's an operation that you can apply. Okay, Samantha, question? Then you ask lah, then ask, who more handsome? This one or that one? This one, right? Obviously. Correct or not? This one handsome, right? Not very handsome, right? This one more handsome, so must ask this one, okay? So how? Tell me, yes, what question? Yes, just now, wow, no reverse. Hey, you want to ask more timely, not timely way, just now to where, back check. Where, sorry, we go back first. Hey, why is that? Hey, it's stuck. This slide also. Which slide is it, Because once you apply, it already disappeared. What's deferred operation? Deferred operation is an operation whereby you cannot actually execute it until you're waiting for something else to happen. Because the point now is this operation, you have two pieces, right? One piece is done, one piece is not ready, then you can't apply it. If basically once you hit only finish already, right? Okay, so it's not deferred, because it's not waiting for anything. Immediately, correct. Correct. No, it doesn't replace. It just that's the wrong way of saying it. Once the if evaluates the predicate, right? You evaluate either the consequent or the alternative. Okay, that's what it happens. Yes, next. Very good question. The question here is the following. Very early, Mr. Lee. Hello. Okay, so the question here is this: can we replace the null items with the items? Cannot. The answer is can, in the sense that won't give you an error . No, it's not ugly. It's worse than ugly. What's the problem? Anything that is not false is true. Woohoo! How fun is that? So what happens? That means your procedure almost always isn't null, because the thing you put in there is not false. So it's going to be a problem. Which one? You want to replace this thing with a NULL. Yeah, of course can . Why can ? Because items is null I mean, of course can. Yeah, it still can . I mean, there's no difference, right? I mean, because okay. So the question is this: you want to replace this thing with the items. The answer is yes. Because this thing and items are the same equivalent. I mean, they're not the same, they're kind of equivalent, right? They're just null pointers, so it's okay. But if you replace this whole thing with items, then life is complicated, right? Okay? Alright. Okay, examples. Okay, so just say you map what's ABS? Apps, No. Absolute function, right? So, basically, you replace apps, you map apps on this thing, you have what? 10, 2.5, 11.6, whatever, okay? Very simple. Square this, you have the square, right? Okay. Cube, same thing, right? Simple, So mapping will do what? We'll take operation, we'll apply it to every element, we'll return a list where the operation is applied to every element of the original list. Very simple. Yes? Good question. Map square and square list. Is it faster? Same thing, right? Okay, your question is, this thing compared to, this is actually same thing, right? So no, you're comparing this. I can't go backwards, Tracy, It hits me. Okay. Hey. Yeah. So you're asking me whether whether this thing, the square, he's asking the question now, whether square list here is faster or slower than this thing here, map to square. What do you think? Faster or slower? Why is it faster? Oh yeah, frankly, the code is the same right? The only difference now is one extra function call or something like that. So frankly, it hardly makes a difference. So I would say equivalent. Because the implementation of the code is the same. Right? You're still carrying the thing, coding down the list, right? Okay, the only difference here is now you have extra layer because you're calling it one more time, right? You're calling the thing inside. Okay, so I don't know how the map because of procedure abstraction, I have no idea, right, how Dr. Record actually influences map. And neither I care, okay. But my point is, based on the code I've given you, they are pretty much equivalent. Okay? For me, I won't care about these things where it's plus minus one step, two steps. I really don't care. All I care about is the big O, right? Whether there's a difference between n and n squared or something like that. I mean, I care about this kind of asymptotic behavior. Okay, if it's plus minus one step, two steps, I really hardly care. As far as the computer is concerned, it hardly makes a difference. Right? Okay, so good question. Anything else? Okay, Samantha, you're all done. Hey, remember, next time question, ask this one. Okay, not that one. Thank you very much. Okay, good. Next thing, now we'll go into this fun thing called tree. Okay. So, a proper list is a whole chain of cons pairs that terminates with a noun, right? Okay. It turns out that recursion, right? So each of the pointers in the whole chain could also point to list, and those could also point to list as well. So essentially, okay, if every single the general idea is this. Now, if you follow this whole chain, okay, if every single chain of pointers, okay, occurs such that the last CUDA pointer is always a noun, okay, on every branch, then this thing is called a tree, okay, and the printout will not have any dots. Okay, so basically you take a structure, a con structure, you print it out. If you see dots, it means the guy is not a tree, right? Okay, but if it's not if it's a tree, then you only see parentheses and there will be no dots. Okay, simple. All right. So this thing is okay. Cons list 1, 2, list 3, 4 is actually a tree. It looks like this thing, right? So essentially there's the cons box here. This is the cons. This thing here is the cons. Okay. List 1, 2 gives you this thing, right? And this 1, 2 is the car. And then 3, 4 will be the CUDA, right? So this is the structure you will see for this particular piece of thing. Alright, so the interesting property is this thing called closure, which is that basically when you cons something that is of a pair, you will still be a list, right? Okay, so good. Alright, sanity check. Okay, now we take out the clicker time. Okay, you do get EXP for clicking. How fun is that? And I also know who missed lectures. I never figured out what that is, but it's okay. So now let's just make sure you understand. So suppose you have cons list 1, 2, list 3, 4, which is just what I showed you. What is the length of X? Yes. I don't understand the question, but you can talk to me later. Okay, I'll talk later. Okay, next. Okay, so are we all there now? 35. Okay. What's the answer? 4, 3, 2. Okay, really, all done? Okay. Whoa. So the answer is 3, Why, Okay, because you see, the first cons box is what? The car goes to these 2 pieces, right? This is the first element of the list. Then after that is what? Is 2 more pieces, right? So when you do counting length, what you do? You do re mi until the end, until the noun. So there will be 3 pieces. Okay, Next. Okay, so count leaves, that's what? Count leaves, count the number of leaves in a tree. So how many leaves? Hurry up. You don't understand, right? Don't write something, No, count list, I just told you, count list, count number of lists in the tree. Okay, what are lists in the tree? Okay, you saw the structure now, right? Try something now, it's okay. Hurry up. How many are there? 35 of you, right? Okay. Are we there? Yeah. Okay. So answer is 4. Okay, correct. So that basically they are in this structure. Okay. You have 4 leaves, essentially, right? Okay. This is just so this tells you the difference between the length and the leaves. Okay. Leaves is going to tell you how many non-null pieces of stuff that's actually out there. Okay. Next. What does this look like? Cons 1, 2. How does it print it? List XX. It's option 3 missing parentheses. Answer is, answer is 3. Okay, the point is not missing parentheses. Okay, so the thing here is this: if it's cons XX, then things are different. This is list XX. Okay, so you're section number 3. Excellent. What? Yeah. So the point is this list, okay, list XX has how many elements? What's the length of list XX? 2, and the elements are, this is X and this is X. So the answer is 3. Okay, what's the length of this thing? Not the above. Hurry up. 22, 24. None of the above. Okay. Okay, the answer is none of the above. I just said it's not explicit answer. The problem is that the list here has how many elements? 2, okay? The elements are X and X. Now, so let's ask the question. Suppose I do cons XX, how many elements? How much the length? 4, right? Okay. Why 4? Go figure out yourself, Okay. So count leaves, how many leaves? Oh, you got it. Da-da. Who didn't bring the speakers? How many are you? You lose the speakers. You have speaker now, right? Okay. All right. Have you done that? Sorry, 33, 35. Okay. Answer is how many? All right. Very good. Okay. So there are 4 leaves in X. There are 4 leaves in X. Add together we have 8 leaves. Okay. Yes. Good question. The question now is why is it 2, right? Why? Because the way, okay, remember how length works, right? Length does what? Takes the car, adds 1, right? Then cool down the list, right? And then takes the car, adds 1, cool down the list, right? You end when? When the thing is now, right? Then you get 0. So over here, when you list XX, you basically do twice and you're already finished. You will do, first one is the X. You return, the first car is X. You cool down the list, then you have the X and the now. You take out the car again, that's 2. The next one you have the now, so answer is 2. Okay? Alright, so this is the answers. So this is the structure, gentlemen. So this, essentially, to know that basically 1, 2, 3, 4 of this is X. Okay? So this is how it looks like. So these are actually 4 leaves. Okay? Yes? No, not missing. This is right. Yeah, so the trick is that this is not cons, this is the list. This is okay, the whole point of this exercise here is to confuse you. You all know, right? I mean, you read this article I posted, right? Basically, if you're confused, you will learn better. Okay? So here, okay, there are a few things to confuse you about. There are 3 things, right? There is a cons, there's a append, there is a list, right? Okay, and so you all must go back and muck around with this thing, open double scheme, try a few things, list, cons, and append, okay, and try to figure out what in the world is the difference between the 3 of them. They are different. Okay, and it's not that hard. You just have to wrap your mind around it, and the way to try to wrap your mind around it is to figure out this cons boxes. That's why I give you the box and Venn diagram. Okay, so next thing is, so I just told you count leaves, right? So just now count leaves was really kind of what you call wishful thinking. Yes, sir. Correct, but all the branches doesn't end in noun. All maybe not right, maybe less. I mean, the branches they go over the shop. Somewhere must always end in the noun. Means everywhere you must end in the noun. So if you have a CUDA pointer point non-noun, then life is not good. No, list 3, 4 will have 3. Will have first thing. List 3, 4 how many cons boxes? 2. One cons box points to the list 3. One cons box points to 4. The CUDA points to noun. So it's not true. Okay, so anyway, this is how you count lists. Answer is not length. Length not good enough. It's called what? Recursion. Very good. You see, clever boy. Okay, so very simple, right? Every question here you answer with recursion. How hard is that? This class is so simple, right? Don't you think? Okay, so first, what's the base case? If it's now, is it now or not? Da-di-da, no, right? Now it's not now it's one case, but what else? Let's see what. If it's not a pair, okay, let's get 3 empties now, okay, it's 0. Otherwise it's what? If it's the card may also be 3, so how? You check whether it's a pair. Okay. Sorry, the car may also be 3. So essentially you must actually do what? You must actually add the count list of the car to the count list of the CUDA, right? Okay. So it's also possible for the car or CUDA to be a leaf. So you must do what? You must check whether it's a pair, right? If it's a leaf, you add 1. Okay. So the idea is this. Okay. If the tree is empty, of course it's 0. Okay. But other than that, if the CUDA cannot see the tree, so you CUDA down the tree, the tree. Another thing is that the leaf is the tree is the leaf, then you count as 1. Okay, that means the following. Now first now is 0. Now then you must check whether it's a leaf. Okay, and the way is right. I said this. To check whether the thing is a leaf, you check whether it's a pair. Okay, now if it's a pair, it's obviously not a leaf, right? So the case it can be now. Okay, but that will be 0. Then the thing is that if it's not now, then it's not a pair, then it's a leaf. Okay, other than that, if it's not either of this thing, what do? You add the car and the CUDA. Simple? Okay? Okay. Right, so next, okay, so this one, next we have the example whereby we want to scale, okay, just now what we showed you was how to scale what? A list, right? Now it's a bit different. Now we want to go and scale the entire tree. So you want to traverse the entire tree and make sure you double or triple every single leaf. Okay, so how would you do that? Again, recursion, obviously, but how would you do this? Let's take a look. So scale tree, my tree, okay, my tree is supposed to be this structure, this nasty structure here. I want to scale it by 10 to give you this structure. Okay, so the idea is this, the tree is a list of lists, right? So what you'll do is that you want to map over each element in the tree. Okay, so how would you do that? Well, each element is possibly a subtree. Okay, so you must recursively scale that and return the list of results. Okay. Base case is what? If the tree is a leaf, or it's now, okay. If it's leaf, you have to return the leaf. But then so the thing, that's this idea. Okay, so the idea here is this: you scale tree, okay, the tree plus the scaling factor. What you do is that you do a map on each element of the tree. Okay, think about it. The tree has a whole bunch of const pairs, and every single thing can point to another massive structure, right? Okay, so the lambda takes in what? Lambda takes in a subtree. Okay, now the subtree has two possibilities. One possibility is the subtree is just a leaf, and the way you test for leaf is, okay, nothing to learn here today, is that not pair will test for leaf. So the element is actually not a leaf, it's not a pair, so it's a leaf. You multiply the element by the factor. The other possibility is that thing you took out is a tree itself. Then what you do, you basically take scale tree and you apply recursively onto the element. The method looks kind of in pain. So okay. You put pair subtree. Question. You put pair subtree reverse 2. What did it say? Hello? Anybody? Okay. Question here, very quick question. The question is the following. You get rid of the knot. You flip the two around. Are they the same? Who says yes? Ms. Tong? Understand the question? No. Question is this. You delete knot. You take this guy, you swap them around. Is it the same now? Yes? No. Not the same. Yes? You guys just vote? No. Eugene? Still thinking, you have nothing faster now. Same right? Same lah. Hello, same thing lah. I mean, the thing is that you just set the two orders, same lah. But the reason why we do this is because it's more natural lah, right? The natural thing is because the point is that again, this is for pedagogical semantic reasons, right? This is like a base case, right? Because not a pair, the leaf like a base case, so we put it first. Okay, typically you near the base case, so you call the thing, yes. Good question. Excellent question. How come I did test twice now? That's a map or test now. Excellent. So it's hidden inside in the map. Excellent. So this side, there's a lot of subtleties. Very cute. Okay, obviously, these things actually happen. So if you look at a tree, you know it tests for these things. Okay, but you don't need to test for this because actually it's done in the map itself. Excellent question. Next. Okay, good. Alright, so compare this with this. Okay, so this is counties, this is the scale tree. So it's a little bit different now, okay? So and how are they different? So let's take a look. Okay, so what I want to do now is make sure you appreciate some of these things we're doing. Okay, the two of them are similar but not quite the same. Okay? Okay, both of them, both of these operations they are actually spanning the entire tree, right? Has to be, right? Count tree must go to every leaf and figure out how many leaves, right? Scale tree must also go to every leaf and then actually figure out actually do the things on the leaves, right? So, but it is different. So let's have some appreciation. So how does scale tree do it? Okay, scale tree is like this. Okay, again, hopefully Miss Samantha less pain after this thing. So this is the definition of scale tree. Okay, essentially you're doing what? You're mapping this blue stuff onto the tree. But actually you're not really mapping on the tree. You're mapping onto what? A map operation affects what? Actually a list, right? And this is the list we are talking about. Okay, so what's happening here is that you're mapping this thing onto this top list. Okay, so suppose you do scale tree 2 okay. Now, so and how does map work? Map actually operates on the one car at a time, right? So you're applying this thing, which is the blue color thing, onto this car, right? This car becomes a subtree. It turns out what? It is actually a pair, right? This is a pair, so this one will fail, right? So you end up doing scale subtree this thing. And obviously you apply to this thing and everything goes, is cool, right? Okay, I won't go into details, but you will go into the individual pieces. Then you apply to this thing, right? But this thing, when you apply this lambda, you realize that it is actually a subtree, right? So this one is also true, this is true, so this one becomes a true, and then you have this thing, and it becomes this. Then it goes to this thing, right? This thing will be true or false. You actually become true, right? Because this is actually a pair. Okay, so you actually apply scale tree subtree to this thing. Okay, obviously, then you apply this thing to this thing here, and you become this, right? Okay, so this thing is similar to the other thing. Okay, so the point here is to illustrate to you how map goes piece by piece, takes a piece, goes down, recursively handles the car. Are we clear? Okay, this is map. Okay, all watch. Okay, watch. Now, next thing we'll look at is count leaves. Okay. Now, count leaves, similar. Count leaves can obviously reflect the same tree, right? Okay, but count leaves is a bit different. Count leaves does the following. Count leaves basically takes the car, applies count leaves, takes the CUDA, applies count leaves. Okay. So they are both recursing down the data structure, but their recursing in slightly different ways. Okay. Obviously, so what count leaves does is that it takes the car, it applies count leaves, it takes the CUDA, it applies count leaves. Okay. And then how you do this? Basically, again, you take the car and the CUDA, you add together. Okay. So and then this one again, this is the tree. Okay, but it's a kind of generic tree. Again, you apply count leaves to this thing and to the noun. Okay, and this is done. Okay, are we clear? Okay, so the point here is not memorize what count leaves does and what map does. The point here is understand this kind of recursion, that you can recurse using map, whereby some recursion like this. You can also recurse in the tree-like way where you do the car and the CUDA separately. Okay, cool, right? Yes. It will affect the order of growth. Good question. So this kind of question, which order of growth is higher? What do you think? Count leaves and scale leaves, scale tree. What's the order of growth? How did you compare? The spacing you need to be more careful, but the spacing, Richard is probably right, because of the one is recursive, one is map is also recursive, right? Yeah, actually, it depends on how map is defined now, okay? But the point now is that, okay, intuitively, time will be same, right? Why? Because you reach every leaf. Oh, so intuitively, the time cannot be very different. Because, okay, so I say again, what I'm trying to show you is that the way you recurse the thing, eventually, it's basically how you divide the problem and how the trees are traversed a bit different. Okay, but time should be similar because the theory here is that you need to reach every leaf anyway. Right? And the step to reach leaf is similar one because it's the same. You follow. Okay, a tree. You know one thing. A tree has what's the property of a tree? It has no what? no cycles. So which means that every single element can only have one way of getting there, right? So essentially both recursions must essentially have a similar way of traversal and the amount of cost will be similar. Okay, the space depends on the implementation, so you can't really say unless you know what map does and things like that. Okay, but the general idea is time they should be similar. Understand that? So you all should have this kind of intuitions for this kind of work because you must understand what roughly it does and have some intuitions for how it does it. Okay, so the basic principle here is the thing that inside here is that you must reach every leaf. So sama. Okay. It depends. Just the pluses may end up pluses will be so longer. So the depth. So the space typically is about n, right? It will be the depth of the it's not n. Space will be the depth of the traversal roughly. Okay, I tell you what. Now when you go on to the class, okay, the space one, why don't you guys do as homework? Go and look at it more carefully because I need some time to also imagine and think about it. But it will not be more than the depth typically. But be careful. I mean, you think more carefully what it does. Okay. So the general idea is this. General idea to figure out space is what? Is to do some simple examples. Look at how it expands. Okay, and the general idea is to figure out how many deferred operations you have at the maximum point. Okay? Good question. Alright, now next thing I want to talk about something very important to digress. So this is concept equality. Hello, good morning. Okay, so what does equality mean? Anybody? Same, right? Okay. So it turns out there are two possibilities. There's this concept called identity. Okay, I say again, identity, and which means that they are the same object in memory. Okay, they are exactly the same object. Okay, and in scheme we use this thing called EQ question mark to check for this. Okay, so you have two objects A and D. For them to be EQ question mark, they must be the same object. Okay, what is the other possibility? It's called equivalent, which means they look the same, they smell the same, but they're not quite the same object possibly. Okay, so this means that two objects are equivalent, even if they are not the same object. Okay, and in scheme we use the predicate equal question mark to test. Okay, question. Okay, you all know this, right? Yes, what? It's true lah, but you understand what I'm saying, right? Equivalent lah, they are the same lah. They're not the same, it's true. So identity means that they are the same exact object. Equivalence means that they could be the same object, or they could be different objects, but they're kind of similar. Okay, let's look at examples. Yes, John, can you what? Yeah, that's what I said, right? Memory location, right? Okay, let's look at this example. Okay, so let's look at example to make sure you understand what it means. Okay, so there's some objects in memory which are like X, Y, Z. Okay, they point to two different lists, A, which are A and B. Okay, there's a way to define lists. Instead of using the annoying like open parenthesis list something, you can use this thing called the quotes, which we'll cover Friday. But for now, just believe me that this works. So you define X, AB, Y, AB. You have these two things in memory. Okay, and then after that, I define Z or Z to be X. Okay, so once I do this, right, I basically have this kind of a structure in memory. Okay, so there are three variables X, Y, and Z or Z. Okay. And how many people say Z? How many say Z? Z. Z. Okay, very good. So this is the Americans versus the Brits. Okay, so hardly matters. I'm kind of confused. Hey, so what did the New Zealanders do? Z. Z. Okay. Z. Okay. Alright, so very good. Okay, so anyway, this is what it looks like in memory. Okay, next thing. EQ of X and Y will be false, because X and Y, they point to different locations in memory. Okay, so the way you see this is the following. Obviously, X and Z or Z or Z, they point to this point, same point in memory. This guy points to here, this guy points to here, so they're not, it's false, EQ. Equal XY, answer is true, because the two fellas look the same, right? They're both, open parenthesis, A, B. Okay? EQ, X and Z and Z, Z is true, right? Because they are pointing to the same place in memory. Okay? Equal, these two things are obviously true, because they're the same object actually. Okay? Y, Z will be, Y is here, this one obviously is false, these two obviously is true. Okay? So this hopefully illustrates to you what is equivalence, identity. So yes, it's true. I'm not a professor of linguistics, or English teacher, so I'm not so good in language, but hopefully this is good now. Okay? Alright, good. Any questions? No, alright. Samantha, okay now? And you have to tell me now if you want to clarify and tell 3 slides later. Okay. No. Memory location is determined. There are two concepts here. There's EQ question mark, which is identity, and there's equal question mark, which is like equivalent, right? So EQ is determined by the memory location, whether the 2 pointers point to the same place. Equal checks whether they are similar things. I mean, a list of 1 and 2 is similar to a list of 1 and 2, equivalent to 1 and 2. Okay? Can? Okay, the last thing would be 3 will be true. Okay? Okay, so this is the thing. Please do not use EQ question mark to go and compare numbers and characters reliably. Because it may turn out to be the same, it may not turn out the same, it's hard to say, okay? A bit annoying. Okay, so EQ should basically be used to compare objects only. And equal basically should be used to compare like equivalent, because they will return true when two things are kind of equivalent. Okay, let's take a look at this. Now, if you do equal apple 1, 2, 3, apple 1, 2, 3, answer is true. Okay, now if you feel like it, you do EQ question mark apple 1, 2, 3, apple 1, 2, 3, the answer is false. Because what happens in the second line is that you generated 2 different lists. Okay, and they will be residing somewhere in memory, you have no clue where, but they're not the same place. Okay, so it'll be false. Now, the other thing is that if you have the next thing, EQ this thing, EQ this thing, equal this thing and this thing, the answer is false because they don't look the same, right? The structures are actually different. Are we clear? Okay, simple. Okay, that's good. Next. Now, it turns out there's a third thing called EQV question mark, which is a little annoying. Okay, to be honest, this is definition. To be honest, I don't even know what it is, because it's too pain behind. Okay, basically it's implementation dependent and more expensive, and don't use this. Okay, more sorry, don't use this. Okay. No, because the point is this: EQ question mark and equal question mark are sufficient to do whatever you need to do. EQV does some stuff, okay, which is a little hard to remember. Okay, and not very natural, and you don't really need it, so try to avoid it. Okay, and you will not come in the exam. If you want to go and write your code in a practical exam with EQV, you carry on. If there's a bug, it's your problem. Okay, but typically any of the code in this class, EQ question mark and equal question mark sufficient. Okay, because these two have very, very, very well defined definitions. Okay, questions? If you use EQ question mark to numbers in exam, you probably won't. Except numbers, you use equal or something, use the equal sign. Right? Okay. And typically, you don't use, okay, the thing is this, your numbers, you typically use equal sign only for what? Integers. So if your numbers basically have this floating point kind of operation, you typically don't use equal because it's very easy to end up missing the thing. Okay? Yes. No. Right. The equal sign only works on numbers. Okay. You try equals and try your luck, no? But two floats are very likely, I mean, oftentimes not the same, Yeah, so, okay, floats typically, okay, sorry, let me explain to you quickly, Floats, you're testing on floats, typically you use greater equals or something like that. Or else you use something like tolerance or something. Basically, you say equals to this thing is less than, within like some finite 0.01 whatever lah, okay. Saying equals is very, very scary thing to do, okay. And it's very hard to find. I say again, okay. So if you all want to use steps to equality with a number, okay, and if you're very sure the number is integer, it's okay. Okay, and later you do whatever. There are some object types that integers, those are okay. Because integers are quite equivalent, right? The problem here is the float. Using the equal operator on floats is a very scary problem. Okay. Next, okay, sanity check. Go back and do your homework. Do this in your forum. Okay, the question now is how do you do this thing called copy list? Okay, you take a list, return a copy. Okay. Note that this is not acceptable. So you do a copy list. L, and then okay. Because it's not copy, I mean, so this one basically, you want to do this, okay, define a list with 1, 2, 3, and then copy list L. You EQ one copy will be what? False, Okay, so the whole point is the same. So EQ, equal question mark, the two things will be true. But EQ question mark, these two things will be false. Okay, now if you do the above, copy list LL, what happens? You'll be both true, right? Because they return exactly the same thing. It's not a copy. Okay, so this thing you must go and figure out. Good question. Go and try. See, can or not? You're gonna try. Okay. So at this point it's time to take a break. Okay. Listen, and I will show you 2 clips today. Okay, the first clip. Have you seen this before? No, okay, it's cute. Okay. Okay, so another one that I want to show you, this is basically in honor of Richard. Okay, you'll see why. Okay, how many of you know Cantonese? Cantonese. Okay, very good. Let's take a look at this. It's very cool.
Hãy subscribe cho kênh Ghiền Mì Gõ để không bỏ lỡ 感情我夜裏合說飆過，懷着冷卻了的心窩飄火，風雨裏追趕，霧裏心不正煙中，天空海闊你與我可會變？再變，原諒我這一生不羈放縱愛自由。哪會怕有一天會跌倒？背棄了理想，在人都可以。哪會怕有一天天這降落？仍然自由自我，永遠過着我歌，手邊。不羈放縱愛自由，也會怕有一天會跌倒，背棄了理想，誰人都可以，哪會怕有一天天野降落？背棄了理想，誰人都可以。
Okay, I just thought it was really cool. It was quite cute singing Catholic song. Okay, so maybe Richard can sing for us something at the end of the class, right? So anyway, it shows that it's possible to do some of these things. Alright. Okay, so now that we have listened to music, right? Okay, so basically you've heard some music, okay? So let's take a look at how music works. So music, typically you have some sound wave producer, typically some Walkman or CD player, whatever. Then you go to the amp, and then you convert it into sound waves, right? And you hear them. Okay, so this is kind of what you would consider some kind of a signal processing view of sound. Okay, so it turns out that what you can do is that you can go and put in some additional components, right? You can insert some kind of filter, or equalizer, whatever, you filter out the high frequency, low frequency, and then you can do this. Okay, and the thing is that you can also change components. You can basically swap out some of these components. Okay, so the thing that I want to highlight today is that these components sort of interface with each other through this thing called signals. And it turns out that this basic concept is also applicable in programming. Okay, so how does it work? So the general idea is this: we can actually model computations as a kind of a signal processing framework. Okay, so if you see the earlier picture, right, there are a few kinds of operations that you can perform. First is the producer. Basically, you can produce a signal. Okay, and then you can filter stuff to remove some elements. Okay, you can also map things. Map is just what you saw earlier. You take a whole bunch of elements. You apply the one function onto each element, right? And consume, basically, you can actually accumulate the signal. I'll show you examples soon. So the general reason, the reason why you might want to do this is because of the following. First, modularity. So you can reuse components. You can actually modify them, whatever. Okay, replace them. Clarity, basically, it allows you to see the whole processing framework more clearly. Okay, we'll see examples shortly. And flexibility, you can add new elements. Okay. Okay, let's take a look. Suppose I want to sum the square leaves. Right. So given a tree, suppose we want to add the square of only the odd leaves. So suppose you have the list 1, 2, list 3, 4. So this is a tree. Okay. And the thing is that there are how many leaves here? 4 leaves, right? How many of these are odd? 2, right? 1 and 3. So what does this do? You want to take the odd leaves, square them, and sum the result. Very simple idea. Obviously, for kicks, you can go and write this thing out. Okay, and this is how you do it. Okay, I won't go into details. Okay, this one you can leave. I just flash this. For what I said earlier, you should be able to derive this. Okay, so go back and try this. Okay, flash, gone. It turns out that the whole point here I'm trying to highlight is this. You can actually look at this problem from a kind of signal processing view, which is the crux of the issue. Right? You can, first of all, enumerate all the 3 leaves. Right? So essentially you have all the leaves. And then what you can do is you can filter out all the odd leaves. Means throw away all the even leaves. Then you can do a mapping operation on remaining odd leaves. And then you can sum them up using accumulate. Okay? So the question now is, how do you represent the signals? So what we do in scheme is that we represent the signals with a list. Okay? Now, so first of all, let's take a look at some of these procedures. I have this procedure called enumerate leaves. Okay? Enumerate tree. If it's null, I return null. Okay? If it's not a pair, which means what? It is a leaf, right? Okay? I return you a list of the tree. Okay? Otherwise, I do what? I append enumerate tree, car tree to enumerate tree, CUDA tree. This is similar to what? It's similar to count leaves, right? Basically, I'm CUDAing this thing and then I'm doing some stuff. What does this do actually? It basically, okay, you do this. If you apply enumerate tree to this thing, what do you get? You get this. Okay? This is known as a flattening operation. Basically, you take the tree, you pound it into a list. Okay? Are we clear? Okay, now, how does this work? Again, if it's not clear to you now, then it's a good thing, you're confused. Go back home and look at this thing until you are confused. Okay? So just know that this thing does this thing. Go back and figure out why it does this thing. Okay? Again, learning it takes effort. I can do my best to try to introduce some concepts. But I can't be too clear also. If I'm too clear, you will think that, oh, it's so easy, and then you have no clue, but you still don't know this. So go back home, figure this out. Very important. Okay, the thing is this. Okay, how do you know whether you know this stuff? You should be able to write this thing by yourself. Basically, in scheme is very nasty. Every single thing you can write yourself, pretty much. Okay, so your level of competency now, after today's lesson, you should be able to. I give you this thing. I tell you this problem. You can write out this whole entire operation. Okay, this is the kind of standard. And you shouldn't be a case whereby you memorize this thing and reproduce an exam. You'll be very, 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 very screwed. I tell you this. Okay, the whole point of scheme is that I give you a problem you can solve by yourself from first principle. Okay, memorizing this thing will basically cause you problems. Okay, so you should be good enough to do this by yourself. So make sure you can do this. Okay, next, filter. What does this do? It's obvious, I mean, I told you earlier, right? You take the predicate and it checks whether or not each element satisfies the predicate. If it does, then it keeps the thing. If it doesn't, it throws out. Okay, so this is the filtering operation. Okay. Okay, so you filter odd. What do you get? 135. List, only list. This only list. This filter is for list. Yeah. So right now we are dealing with only list operations, because flatten has already converted the thing, whatever thing, into a list, right? Okay, so filter will be a list operation. Map will be a list operation. Okay. Can? Okay. You can't. It's one way street, sir. I mean, because given a random list, you can have infinite representation for trees. So it's not infinite, okay, finite. Sorry, it's finite, but quite nasty. Okay, so the answer is no. Okay, flattening operation is quite standard. Okay, the other one is not so standard. Okay. Okay, accumulate basically does what? Accumulate is like what's the thing similar to? Fold. So accumulate is actually fold. Some sort of fold. You put the op, you call the sequence, but this is a fold operation applied to a list. Okay? Okay? Okay, accumulate is like a fold. Okay? So accumulate plus 0, this thing gives you 10. Sure not? 15, right? I can count, right? So 15, Alright, so cons are, what is this? Accumulate cons, nothing. This one does nothing, I get same thing back, so it's just for fun only, okay? So anyway, the point now is that to understand these operations, what they do roughly, okay. So accumulate does two things. Initial is the base, is the base condition. So when you sum, 0 is the base, okay. Op will be the plus, and if you have null as the base, and then you basically const the thing on, you have a list. Okay. So that doesn't do much. Okay. Are we clear? Any questions? Non-EQ. Non-EQ. EQ question mark. This one will not EQ, correct? Yeah. Okay. All right. So, okay, given what we have already said, right? Okay. Given what we said, basically, to do the sum odd squared tree, okay, the general idea is the following, right? It's just to do the following. It's to basically take the leaves, you basically take the tree, you flatten it, okay, to enumerate the leaves, okay. And then after that, you do what? You filter out the odd ones. Then you square all the elements, and then you accumulate with a plus and 0. Okay? So, and then the general idea here is see that this thing, okay, this is the way that's written, right? This way. Okay? You know, this is the way it works. Code-wise, how does it work? Code-wise, it's actually reversed. Okay? Are you clear? The answer, are we following? Okay, because this is the tree, right? You first flatten the tree, giving you a list of the flattened elements. Then you filter out all the odd elements, and then you map square onto the elements remaining, and then you accumulate the rest. So although left to right is how you see the whole process, okay, the way that the operation is written out is actually backwards. Okay? Questions? Okay, clear? Now, so let's just quickly take a look at this. I'll make sure you understand. So 1, 2, 3, 4. You enumerate leaves, it gives you 1, 2, 3, 4 but it's now flattened. Okay? After that you do what? Filter odd, right? Gives you 1 and 3. Then you do what? Square, it gives you 1, 9 and 10. Okay? So this gives you a quick overview about how, given a certain structure of tree, you will go through the process and give you this answer. Alright, so this is quite cool. Next. Okay, now let's say if this is not fun enough, let's do the following. Suppose I want a list of even, okay, fib is a Fibonacci number. Starts with fib 0 is 0, fib 1 is 1, and so forth. Okay, so you want a list of even fibs for all k up to a given integer n. Understand? So means I want to generate a list of Fibonacci. Okay, suppose I give you n, you need to generate a list of all the even Fibonacci numbers up to n. Okay. Now, okay. So, if you want to basically write this so-called usual recursive way, this is how you do it. How fun is that? Okay. I'm not going to go through this thing. This again, you go back home and try to figure this out from first principles. That means you look at this thing. Okay. I give you this problem. You try to write a procedure, recursive procedure, or iterative procedure, whatever, to generate this list, just for kicks. Okay, but this is how it looks. Okay, the first thing you want to realize from how it looks is that it's not particularly obvious that this does the right thing, and you need to basically eyeball it and like a bit annoying. Okay, obviously this works, but the point I'm trying to make today is that obviously even fib 4 will give you 0 and 2. Okay, the whole point I'm trying to make here is that you can take a look at this particular problem, and you can very naturally frame it as a signal processing problem. Okay, so what you do, you basically enumerate integers, okay, from 1 to n. Then you do what? You map fib right onto the integers. So you generate all the list of what? All the fibs from 1 to n or whatever. Okay, you filter out the even one, and then you basically keep it. Okay, so the previous example was this, right? Okay, so obviously what you see here is that I am using the same basic operations, okay, except that the orderings are a bit different. Okay, so the only thing that's missing here is this. The last time what happened is that last time I used flatten, right, to flatten the tree. Now I need to generate integers. Very easy just use this. Right. So this will generate all the integers from a low to high, right? So I can generate like, okay, if the same thing, this is the same as sum, right? Remember? if A more than B, you go 0, right? So if low is more than high, you go null. Otherwise, you const the low onto the enumerate interval low plus 1 and high. Okay, so when you do this, you have this. Okay? So, even fibs can be solved with this problem, right? Okay, actually, if you look at it, accumulate cons is redundant, right? Okay, but I'm just using this to show you the kind of steps that are kind of used. I mean, this maps into the signal processing world, whereby you have the producer, the filter, and then the mapping, and then as well as the consumer. Okay, but this thing is actually redundant. It means without this step, it works as well, because this thing does nothing. Okay, so the general idea is this. The only thing I'm introducing today is basically this concept of actually having some. Okay, there's this set of problems that can be solved either using the typical recursive method. You just write out the recursive process, or else you can actually take the problem and frame it into this particular view. Okay, it turns out that this view basically allows you to kind of deal with complexity. There's not many complexity, right? Okay, if this is a way of looking at a problem that will allow you to solve it in some kind of elegant way, and typically, I mean, I've already given you all these kinds of basic operators. So in the exams, okay, you're not required to remember all these things. Okay, when I say that you're required to be able to copy it out in real time, it's just a matter of understanding. Okay, exams, I will probably give you this definition in the back or something. Okay, so you can actually call these procedures or whatever. Okay. So yeah, so the four key operators, there's the enumerator, which basically creates generates original thing to work with. There's a filter operation, map operation, and the final thing is accumulation. Okay. So the interesting thing is that they're independent of each other. Okay, because they are all linked up via this list. Okay, and they're modular. Okay, so the general idea here is this. Okay, you want to basically create a library of components. Okay, and the general insight is that you can use lists to interface between components. So every component has a following I/O, right? The input is a list, output is a list. Except accumulator. Accumulator output is a something, may not be a list. Okay? Okay? Okay, so suppose I want a list of squares of fib k. How do I do this? Just for practice. First thing I do what? I will generate the list, right? And then I do what? I will do a map, right? And then I'll do what? A map again, right? And then I do what? Actually, it's all okay. This is actually redundant. Okay. Now another thing, example, I want to have suppose I have a sequence of personnel records, okay, and I want to find the salary of the highest paid programmer. Suppose that. Okay, you will look something like this. Okay, essentially you take records, you filter out the programmers. Okay, you will map salary to draw the salary, right? And then you do okay, it's interesting. Accumulate max 0. Make sense? No. Negative salaries. It doesn't make sense, I agree, but then it probably doesn't make sense to negative salaries for programmers. You don't have programmers and morons, right, working for you. I mean, okay, so you work for me, I give negative salary. How is that? I like the idea of that. Okay, so typically you expect the programmers not to be morons and they don't take negative salary. So this one should work in general. Agree, right? Okay. So yeah, questions. So the point here is to highlight to you this interesting thing whereby I can accumulate max, okay, and this will actually give me the maximum salary. Right, this is kind of interesting part. So okay, let's see. Assumption here is salaries are all at least 0 lah. Okay, so we're done today. So the summary here is this: lists are actually common data structures, and we accumulate, we manipulate them using the cons, the cars, and CUDAs, right? And then, okay, it's important for you to be able to draw this box and pointer diagram because they really help you understand the structure of this list. Okay. Now the thing is that it's kind of complicated sometimes on how to traverse the list. Okay. And then closure allows you to build trees. Very important to understand the difference between EQ and qual. Okay. And the last thing I covered today is how to look at some of these problems from a so-called signal processing view. Okay. Now any problem you can actually solve with the processing view. Obviously, you can solve by writing a recursive procedure. Okay. Yes. Memory issue. Okay. Good question. Whether it's the memory differences. It turns out you're right. This particular approach could be very nasty from a memory usage perspective. Okay, but we'll cover that in a few weeks in this thing called stream, where we actually do infinite streams of stuff. Okay, it's quite interesting in a few weeks. But memory. Okay, the key difference. Good point. The key advantage of this view of the world is that oftentimes it's easy to think about the problem. But one possible cause is the memory. It may take more memory than normal. Modular as you think about. Okay, so but the whole point is to teach you ways of abstracting problems and thinking about them. Okay, and very good that you highlighted the key drawback, which is memory may be a problem. Okay. Any final questions? The what? Exam up to Friday. So Friday is symbolic computation, I think. Symbolic data, I think, yeah. Alright, so don't worry yet. Okay, any other questions? If not, thank you very much. I'll see you guys. Oh yeah, apparently you have an announcement, right?
Okay, like this is like a thing we do. Like it usually ends up every year that we'll get the students will usually get together and start doing work like together because it usually is required because our missions are crazy. So we were thinking this year of making it a little more like supported, like the tutors will actually be there to answer any queries. We won't tell you the answers obviously, but yeah, we can answer any queries and like maybe help you on your path and understanding the lectures as well. Then if there's like enough people, maybe we can get food and get him to sponsor. Yeah. Then the tentative plan for for now is like tomorrow because mission day is due really soon and some of you are still stuck. So maybe tomorrow at about 6:30, 7. Tentatively we're thinking of like the level 2 area, SR1, or maybe the printer area if there's not enough space. Yeah. So those who need help come. Those who have finished also come so that you know you can help people out because we can't tell the answers. You can. So just come along. As in those who finished already can do their own work there, or maybe like ask about maybe the current lessons instead of like the assignment. So see you guys tomorrow night, I think. I tend to stay in school quite a lot. I just came from Utah. Yeah.
Alright, so it's actually basically assignment. I mean, mission 8 is hard. Who tried already? Okay. And so typically what they do is that they are just chung assignment sessions and in the evening. They try to be more a bit structured. So they want to do tomorrow. They want to organize you to take over the level 2 or the basement area. Okay. So anyway, this is a grassroots effort, not officially part of the class. I leave you to deal with the tutors. Okay. Any final questions? Yes. 101R, no exam. Okay. 101. Okay. One quick question. Sorry, thanks for asking this. So 101R starts this Friday. The room already sent out already like 207 or something. I forget. You check the announcement. Not my problem actually. It's Martin Hans will be teaching. The way it works is that there are like 4 lessons, 1 hour lessons. The NHS guys girls can turn up, but then there's no transcript or nothing because I don't think it applies to you. So the 1R is in JavaScript. You don't think you have enough of programming, you can do JavaScript for 4 sessions. What else is new? Okay, then after that there are also a path. Apparently there will be some JavaScript path which I think Zihan is still trying to build an engine, because the engine for Scream, the engine for JavaScript is still being built. So the general idea here is that if those of you who want to register for 1010R next semester, you are supposed to attend the 4 classes, okay? And you're supposed to finish all the paths, okay? If you don't do either of all, then you don't get to register. And on top of that, you have 2, I think, programming projects in JavaScript. First one to be done after the exam, and second one to be done next semester. Okay, so okay, to be honest, I don't know. Okay, the details I don't really know. I'm just communicating. Okay, this is Martin's baby. I'm just telling you some rough things that I know. You want to know more? You should turn up on Friday. Okay, question? You can't make it, then same thing lah. You can't make it lah, then can't go lah. Today it's okay, I'm done already. Thank you very much. Yeah, so you can't make it, then cannot make it lah. Like exam conflict, then cannot take the class lah. But this side cannot make it, then you can send email to Martin Hans and ask for excuse, whatever. Send email to Martin Hans. Okay, I'm only a messenger, but it's okay. I'm done. Thank you very much. No, it's not this semester. It's registered next semester. I'm taking this semester and over the vacation. No, I told you already, right? You need to do 10 class, do the path, and then you need. You want to say changes? No. Change the yes.
Bye. Thanks. Come down a bit. The gentleman sitting up there. Hello. Hello. Please come down a bit. Sorry, just move down a bit. Don't sit too high up. Thank you.